In this video, I will create an interactive XY plot for an object in projectile motion using Python. What we basically need to do here is to find the X and Y positions of an object in projectile motion at various times and then plot all of those data points in an X and Y coordinate system. So first of all, I need to import some libraries to help me do all of this. The first library I'm going to import is the NumPy library to do all of my math calculations. And the second library is going to be matplotlib.pyplot to use it for all the plotting that we want to do. The third thing I want to import here is slider from the matplotlib.widget library because, as I mentioned, I want the plot to be interactive. So I want to put some sliders on the figure so I can dynamically change the initial velocity and the launch angle and then have the plot to dynamically change as I change my variables. Okay, these are all the libraries we're going to need. The next thing I'm going to do here is to define some constants that I'm going to use throughout the program. The first thing that I'm going to define here is gravitational acceleration. So when I execute this program, a figure will show up. I don't want this figure to be empty. I want a default projectile motion plot already on the figure. So to be able to have that, I'm going to define some default values for my initial velocity and the launch angle, and then I'm going to use those to plot the default plot. So I chose my default initial velocity to be 10 meters per second and the default launch angle to be 45 degrees, but you can have these values whatever you want them to be. Okay, now it's time to define a function in which I'm going to calculate X and Y positions of my projectile motion throughout time. So what do I need here? I want an X position, I want a Y position, and then I want to return them. What is X? What is the formula for X? We know this from kinematics. We know that the formula for X is V0x times t, and the formula for Y is V0y times t minus half of gt squared. So all we need to do here is write down these formulas. Now that we have written down the formulas, you can see some red alerts, some red errors here. Python is basically saying, so what is V0x, what is V0y, what is t? We haven't defined this. So let's define V0x and V0y. Again, from kinematics and trigonometry, we know that the formula for V0x is V0 times cosine of theta, or cosine of the launch angle. And the formula for V0y is V0 times sine of the launch angle. So let's write that down. Okay, so you might be thinking, why did I define the angle to be theta even though I defined the angle up here to be angle? What's the difference? So when we want to do any mathematical calculations, we need to convert the angle to radian first. When we are taking the angle from the user, we're going to take it in degrees because that's how people are familiar with angles in real life. We know them in degrees, but when we want to do mathematical calculations, we need to convert them to radian first. That's why I defined theta here. Theta is going to be the angle after it's been converted to radian. Okay, so one other calculation we need to do is finding t. So for time, I want to define an array. This array is going to start from t equals to 0 seconds up to whatever time it takes for the object to complete its projectile motion. So first of all, let me find out how much time it takes for the object to complete its projectile motion. So to find the total time it takes an object to complete its projectile motion, we need to simply find how much time it takes for the object to reach its maximum height. And then, because the amount of time that it takes the object to reach the maximum height is equal to the amount of time it takes the object to come back down, if we find the amount of time it takes the object to reach the maximum height and then multiply it by 2, we can find the total time that it takes for the object to complete the projectile motion. So what is the time it takes the object to reach the maximum height? For that, we have to go back to our kinematics equations again. We know that del v is equal to negative g times del t. And when we reach the maximum height, the velocity at that point is 0. So we have 0 minus v0y, and that is equal to negative g times del t. And del t from here will be v0y divided by g. And if we multiply this by 2, we can find the total time it takes for the object to complete the projectile motion. So the total time would be 2 times v0y divided by g. Now that we have the total time, let's define the array for time. And you can define the data points to be how many numbers I want. I'm going to only take 500 data points for my time here. Okay, so we are done with all of the calculations I want to do in this function, and we are still left with 2 unknowns, angle and v0, but these are 2 variables that we need to pass to the functions from the user input. Now, as I mentioned before, I want to have some default plot already on my figure when I execute the program. So let's use this function that we just defined to calculate our default x and y positions. Okay, so as you can see, for xi and yi, I call the cal positions function, and then I pass the initial angle and initial velocity that I have defined up here to this function. Now I want to create a figure and axis for my plots. So as I mentioned, I want to have 2 sliders on the figure. To be able to fit that on the figure, I need to leave some space in the bottom for the sliders. So I'm going to do that now. So next I'm going to create a line object for my plots, and then I'm going to initialize it with the xi and yi variables that I defined here, and then later on I'm going to update that line object as I introduce new variables, new v0 and angle variables on my sliders in the figure. Okay, so here I define my line object. Here you can see that I have also defined x and y labels for better readability. And I'm also going to add a grid for better visualization. Okay, now I'm going to create my sliders on the plot. So here I'm creating 2 areas on the plot where the sliders will be placed. Here I'm just specifying the position and the size of the slider. And here I'm actually creating the sliders for adjusting the initial velocity and the launch angle. So before proceeding any further, I need to create a function now that updates the plot whenever the sliders are changed. So let's come back up here. And I'm going to define this function to be update plot. I'll pass the value that I get from the sliders to this function, and then I will define 2 variables, v0 and angle, that will accept this new value from the sliders and store them in these variables. And then I'm going to use this v0 and angle values, pass them to the calculation position function that I define up here, and then calculate my updated x and y positions. So here I am calculating the new x and y positions based on the updated values of v0 and angle. Here I am updating the line of the plot to reflect the new x and y positions. Here I am adjusting the axis limits to fit the new data. And here I am redrawing the plot to update the display. Okay, now I need to connect my sliders to this update plot function that I just created. So here, the unchanged method of the slider is passing the new value that is introduced by changing the sliders to the update plot function, and then the update plot function redraws the plot and then gives us the updated plot based on the new v0 and angle that we have introduced on the slider. Okay, so all is left to do a plt.show, and we are done with our code. So let's execute it. Okay, so there you go. We have our dynamic x and y position plot for the projectile motion. We can change v0 and we can change the angle however we want, and then we're gonna get the updated plot here dynamically. One point that I want to mention is if you increase the angle all the way up to 90 degrees, From physics, we expect that when the angle is 90 degrees, the object should just go straight up and then come back down. There shouldn't be any X position. But here we see a very small X position on the X axis. That is because of the floating point precision error that we have introduced throughout the program, because all of the numbers that we have are floats. So even though we expect the X position to be 0, we still have a very small value for the X position. So there are different ways that we can fix this. And because this is supposed to be a very small program, I'm going to do something simpler. So what I'm going to do is to use a function in the NumPy library called isClose. So what this function does is to compare two numbers or arrays and then see how close they are within a specified tolerance level. So I'm going to write that down here in this function. Okay, so I have it here now. What I'm doing here, basically saying if v0x is close enough to 0 and v0y is close enough to 0, then take both of them to be 0. And the tolerance level I'm specifying is up to 8 decimal places. You can play with this, you can change it, you can make it lower or higher, doesn't matter, as long as there is some tolerance level that would force the v0x and v0y to be 0 if they are close enough to 0. So let me execute the code again. Okay, now you see when I increase this and then go to 90 degrees, now I have the vertical plot that I was expecting. Okay, so this is it for this video. I hope you enjoyed it. If you have any questions, ask me in the comments, and don't forget to subscribe so you don't miss my next videos.